there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we saw the statement of the formula that gives us the surface integral, which is the integral of a real valued function of typically three variables over some three-dimensional surface S. In this video, we are going to do some sample problems to see how we use that formula and what we have to do to calculate the surface integral. So first guy that we have lined up here, we're going to find the surface integral of the real valued function x squared plus y squared plus z squared over S, which is going to be the cylinder of radius 3 and height 4. Now the cylinder, one of our basic types of shapes, this is one of those shapes where you just need to know what are the parametric equations for this cylinder. Unless specified, you can assume that the base of the cylinder lies in the xy plane. So first up, we need the parameterization for our surface S. We need the parameterization for this cylinder. The basic parameterization for a cylinder with a certain radius and a certain height is going to be capital phi hat of u comma v equals, now it's in the x coordinate, it's r times cosine u, but in this case our radius is 3. So we're going to have 3 times the cosine of u. Your y component is 3 times the sine of u. And then your z coordinate is just v. Now the bounds on our variables u and v, we want to make one full trip around the circle, so u is going to go from 0 to 2 pi. And v is serving as the height of this cylinder, so we're starting in the xy plane, or height z is equal to 0, and we're going up to height 4. So v is going to go from 0 to 4. We have our basic parameterization for the surface. We now need to take the partial of this guy with respect to u and v. And it doesn't take too much to find that t sub u, the partial of capital phi hat here with respect to u, is going to be minus 3 sine of u, 3 cosine of u, comma 0. And we also find that t sub v hat, the partial of capital phi with respect to v, is going to be 0, 0, and 1. So not too bad of partials here. Now we're going to take the cross product of these two vectors. As we set up our 3x3 matrix here, we're going to find the determinant of this 3x3 matrix, and that is going to give us our cross product here. And what you find in the end, straightforward calculation of the determinant of a 3x3 matrix shows you that we come up with 3 cosine of u, comma 3 sine of u, comma 0. So this is our cross product here. Now we're going to find the norm of this guy here. So it's going to be the square root of the sum of the squares of each of these components. So we get 3 times cosine of u squared plus 3 times sine of u squared plus 0 squared. We can pull out the common factor of 9 that we're going to get from each of these two terms, and we're left with sine squared u plus cosine squared u. Lovely Pythagorean identity coming back into play here. This is just 1, so we get the square root of 9, or 3. So we've calculated part of what we need to find here. We still have to take our functions for x, y, and z, for each of the x, y, and z coordinates. We still have to take them and plug them into our real valued function that we were given to start with. That, in combination with this guy right here, those two things are going to make up the integrand, and then we can calculate a double integral and figure out what the surface integral is going to be. So formula for the surface integral, double integral over some region D in the UV plane of f of x, y, z, d capital S. Well, our region D in the UV plane is simply the bounds that we had on our u and v variables. We had u's going from 0 to 2 pi, and we had v's going from 0 to 4. Our real valued function was x squared plus y squared plus z squared. So making the substitutions for what x, y, and z were, each in terms of u and v. We get 3 cosine of u squared plus 3 times sine of u squared plus v squared. Now times the norm of that cross product that we just found. Now times that 3. And making sure we place the proper variable with bounds, outside with outside, inside with inside. Just want to simplify this integrand out just a little bit here. Still the double integral from 0 to 2 pi, and then from 0 to 4. 3 cosine u squared plus 3 sine of u squared. That simplifies out to just a 9 by using the Pythagorean theorem once again. So I have 9 plus v squared, and then that whole thing times 3. I'm going to choose to multiply that 3 into both of those terms, and that's going to give me 27 plus 3 v squared dv du. And now this is nice. Now we're down to just a basic Calc 3 type of double integral. Really straightforward to calculate from here on out. If I take the integral of this thing with respect to v, I'm going to get 27v plus v cubed. Top bound of 4, bottom bound of 0. So I'm going to take my top bound and plug it in. When I do, that gives me 108 plus 64, or 172. When I plug my bottom bound of 0 in, I get a nice big fat 0. So this leaves me the integral from 0 to 2 pi of 172 du. This is now just the integral of a constant over an interval. The integral of a constant over an interval is simply equal to the constant times the length of that integral. So that's going to give me 172 times 2 pi, or 344 pi. So there we go. That's our first example of calculating the surface integral of a real valued function over some surface S. You just need to find the norm of the cross product of those tangent vectors, then also make the substitutions for your parametric equations into your real valued function, and then chug away. Next example that we're going to see, a little bit more challenging, a little bit more work to do, but still not the worst problem out there, and we're going to use the same technique, the same method to come up with the answer. We are back here, moving on to our second sample problem here. Now we're going to find the surface integral of f of x, y, z equals x squared plus 2 over s. And s in this case is going to be the portion of the plane with equation z equals 8 minus 4x minus 2y. That lies in octant 1. So we're going to start off the same way. We're going to find that there's a little bit more work that we have to do for this problem. This extra work is going to come down to finding the u and v bounds. So we're going to start off the same way. We need to come up with the parameterization for this surface. Now, our surface is a plane. It's a function of x and y. So we have a very basic way to parameterize a function of two variables. We can write our parameterization as capital phi hat of u comma v is u comma v comma 8 minus 4u minus 2v. You didn't even have to make the substitutions for u and v. You could have just left them in terms of x and y. Still going to come down to the same thing in the end, so it does not matter. Question is, what are the u and v bounds going to be for this guy here? And here's where that little extra bit of work comes in. We're concerned about the portion of this plane that lies in octant 1. So if we picture the 3D plane, and we picture looking down on the xy plane from the top, the portion of the plane that lies in this first octant is going to cast a shadow into the corresponding quadrant of the xy plane. Now, octant 1 corresponds to quadrant 1, so we need to figure out what is the shadow that's going to lie in quadrant 1 of the xy plane. Well, if I find the line where the plane and the xy plane intersect, that will tell us where the boundary, the missing portion of our boundary is for this shadow. So taking 8 minus 4x minus 2y and setting it equal to 0, we find that we get the line y is equal to 4 minus 2x. So I'm just going to give a little sketch of this guy over here. So that is the shaded region that we're looking at over here. That's going to be the shadow of this plane in the first octant. So we need to come up with bounds for this region here. Now we see that when we set up capital phi hat, u's simply took the place of x, and v's simply took the place of y's. So to say that x goes from 0 to 2 is also saying that u goes from 0 to 2 as well. So we could just as easily call these the u and v axes here. And that all comes down to just the substitution that we made. In general, you can't necessarily do that, but for this one particular problem, we can. So I look at this region. If I take any point that lies in the shaded region, the u coordinate goes between 0 and 2. So u is going to go between 0 and 2. And the v coordinate, working from the bottom up, they're always going to start at 0, and they go up until they hit this line. This line has equation 4 minus 2v. 4 minus 2u. So 0 less than or equal to v, less than or equal to 4 minus 2u. So these bounds right here, very important. Star those guys, box those guys. We're going to be coming back to them later on. This is that extra little bit of work that I said that we'd have to do. From here on out, the process is pretty much straightforward as it has been. I'm going to find the partial of capital phi hat with respect to u and with respect to v, and then I'm going to take the cross product of those two vectors. In this case, we come up with some pretty nice tangent vectors. We find that all entries in both these vectors are just going to be some constants. The partial with respect to u, 1, 0, negative 4. The partial of capital phi hat with respect to v here is going to be 0, 1, negative 2. And now we're going to take the cross product of these two vectors. And when we do that, we see that we come up with the vector 4, 2, 1. Again, just another straightforward calculation of the determinant of a 3 by 3 matrix. I'm going to find the norm of this guy, the square root of the sum of the squares of its components. Pretty straightforward, though, to see that. We're going to find that the norm of this vector is equal to the square root of 21. So we have this other missing piece of information that we need. We can now take these pieces, plug them into our surface integral formula, and then just calculate a standard Calc 3 double integral. We need the bounds on u and v. Many problems that you will see, since both of your u and v bounds are both constants, it doesn't matter the order in which you integrate. You could do dv, then du, or du and then dv. But in this particular case, one of our v bounds is in terms of u. So you have to be sure to integrate with respect to v first. So we had our v bounds of 0 less than or equal to v, less than or equal to 4 minus 2u. And then we had u going from 0 to 2. Our real valued function was x squared plus 2. So we're only concerned about the x-coordinate of our parameterization as far as substituting. And the x-coordinate of our parameterization, capital phi hat, was just u. So this is going to be u squared plus 2 times the norm of that cross product that we just found. And then it's dv du. Again, we have to make sure that we integrate with respect to v first because of our bounds here. So this is now just a straightforward integrate away. I'm going to pull that square root of 21 outside of my double integral. And notice that when I integrate with respect to v, there's no v showing up. So this whole thing is just a big constant. So this is going to give me u squared plus 2 times v. Substitute in my top bound, there's some nice foiling that we have to do. Substitute in my bottom bound, we just get 0. And when we do make this substitution, we are going to come up with, in the end, we're going to come up with a minus 2u cubed minus 4u plus 4u squared and plus 8. And we still have to take the integral of this with respect to u. Now just down to a basic Calc 1 integral. Integrate. And when we integrate, we get negative 1/2 times u to the 4th minus 2u squared plus 4/3 u cubed plus 8u. If we take our top bound of 2 and plug it in, we're going to get some stuff. If we take our bottom bound of 0 and plug it in, we're just going to get 0. So we just have to see what it all boils down to after we plug in 2. So we have the square root of 21 times negative 1/2 times 2 to the 4th is a negative 8 minus another 8 plus 4/3 times 8 is 32/3 and then plus 16. And a whole bunch of these terms cancel out, and we're just left with 32 times the square root of 21 all over 3. So this is our second example of calculating the surface integral, the integral of a real valued function of 3 variables over a 3-dimensional surface S. Next video, we're going to be taking the integrals of vector fields over surfaces when we talk about flux integrals. If you have any questions or comments, be sure to leave them in the comment section below. Otherwise, until the next video, take it easy.